Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are finishing up Chapter 7, Equations of State, and we will be looking at what do you do about liquids, and then also how do you decide which of these equations to use. So first of all, there are some generalized correlations that are specifically developed for liquids. One of these is the Racket equation, which is for saturated liquids. So for this one, VSAT is VC times ZC, and the ZC is raised to the 1 minus TR quantity raised to the 2/7 power. If I want ZSAT, then I'll basically take that expression multiplied through by the P's and T's, right? And so ZSAT is PR over TR times ZC to the 1 plus 1 minus TR to the 2/7 power. If I'm not at saturation, if I have a different temperature or pressure, then I can use the Liderson chart. Now for the Liderson chart, we're going to it's done in terms of reduced density, which is density divided by critical density. But remember, density and molar volume are reciprocals of each other, so it's VC over V. And I can use this then as a function of PR, which is across my bottom axis, density on the vertical axis, and different curves for varying values of T sub R. And so I could look up for my pressure and temperature and read across to get P sub R. If I have these, then I can use the ratio of the densities I find from this at state 1 and at state 2, multiply that times the volume at state 1, and that gets me the volume at state 2. The reason that math looks or feels a little wonky is because, remember, density is the reciprocal of volume. Now we want to try some examples with these just because they just feel a little stranger. Now in the ChE 2100, our mass and energy balance course, the specific gravity of acetone at 20 degrees C and 1 atmosphere is given as 0.791. And they also tell us that TC is 508.0 Kelvin and PC is 47 atmospheres. And so based on this, can you find the volume in kilograms per cubic meters? T sub R, well, 20 plus 273 divided by 2C, that's a plus, which is 508, says that TR is 0.5771, and P sub R is 1 atmosphere divided by 47, so 0.0213. Calculating B naught from the virial equation, 0.083 minus 0.422 over TR to the 1.6 is negative 0.934, and B1, 0.139 minus 0.172 over TR to the 4.2 is negative 1.592. So this is looking at it as a gas. B prime PC over RTC is negative 0.934 plus omega. Oops, need the data for omega. Omega is 0.307 times negative 1.592. And so, let's see, this is negative 1.4227. Z, therefore, is 1 plus that answer times PR over TR. PR is 0.0213. TR is 0.5771. So Z is equal to 0.9475. V, therefore, is ZRT over P, 0.9475 times 293.15 Kelvin over 1 atmosphere. And then R, let's see, if I use 0.08206 cubic meter atmosphere per kilomole Kelvin. And in this particular case, the molecular weight of acetone is 58. So 58 kilograms per 1 kilomole. I end up with V is equal to 0.393 meters cubed per kilogram. And this is for a gas. Next, we want to look at acetone, same basic given information, but we want to know the saturated liquid specific volume at 20 degrees C. So for this case, we want to use the Racket equation. So the Racket equation says that V saturated is VC ZC to the 1 minus TR to the 2/7 power. Okay, TR, now I need some additional data to use this equation. It is available in certain data books, certainly not in all. I looked these up online. VC for our acetone here and ZC are given above, and so if we plug these in, my units are going to come from the VC. I'll take my ZC and raise it to the 1 minus 0.5771 power raised to the 2/7. And I came up with about 0.0012 cubic meters per kilogram for this liquid. So now, what if we look at 100 degrees C and 50 atmospheres as a liquid? So in that case, I'm going to need to use the Liderson chart. And let's see, so TR is about 0.734, PR is 1.06. And if I look on the graph for the Liderson chart, it looks like rho R is about 2.53, and therefore VC over V is equal to rho R. V, therefore, is VC over rho R. VC, we found, was about 0.00366 meters cubed per kilogram. Rho R, I just found to be 2.53. Therefore, the volume under these conditions is about 0.00145 meters cubed per kilogram. So finally, how do we make decisions? Well, first of all, we need to know whether we're talking about a gas or a liquid. So in the examples I just worked, I started with a gas, and so I had used the virial equation. But I had several other choices, right? I could use the ideal gas law. Do I believe that the pressure is very low? Then the ideal gas law may be appropriate. Or I could use the virial equation of state. Mathematically, it's fairly simple and direct, especially if I'm only using the two-term one. But remember that that's only going to be valid if the pressure is less than 1 atmosphere. A cubic equation of state may give me very good results. It's going to work best for molecules that are not polar, okay? If I have things that have extreme attraction or repulsion to each other, it's not going to work so well. This tends to work brilliantly for like alkanes, alkenes, those simple, straightforward hydrocarbons, and not so good for salts or electrolyte solutions, I guess, really not salts, or it's not going to work quite so well for polar compounds, etc. Lee-Kessler tables are actually pretty good, but they're cumbersome to use. And generalized equations are the mathematical equivalent to the Lee-Kessler tables. All of these have their place. It depends on how much effort you want to put into them. And when you get to looking at molecules that are in mixtures, then we'll have some additional decision making that we might do. But if all you're wanting to do is a rough check to some calculations that have been done somewhere else, maybe an ideal gas is all you need, okay? So you'll need to make a decision about how much effort this calculation is worth. Again, if you're doing something as a double check, you want to use something fairly simple to use. For liquids, well, we haven't even discussed all of the options in here because our first option is just assume it's incompressible. And so therefore, saturated liquid properties are close enough. But when you need something that's better than that, then if you have alpha and kappa data, using those will actually get you great results. I really recommend it. When you don't have those, the Racket equation or the Liderson chart can be very good. Racket is only for saturated. The Liderson gets you for liquids off saturation. And the cubic equation of state, it's really not very good for the liquid phase. It can be used there, and you will see people do it, but it is probably your worst choice for liquids. So this wraps up our study of equations of state for pure substances. Like I say, in our next course, you will be looking at equations of state with a lot more depth because we'll need that when we start looking at mixtures. We have one more chapter to go for this course. I'll see you in the next video. Thank you very much for your time.